So in this lecture, we are going to see about the Fourier integral. So we'll be seeing subsequently about the Fourier transform. Fourier transform is probably used in the case of signal analysis and all those things. So the Fourier integral, however, is used to solve some integrals. Fourier integral. So the Fourier integral is nothing but Fourier integral. If f of x is piecewise continuous, the differentiable and absolutely integrable. So that means it just means that it is an analytic function. So in minus infinity to infinity. So it just means it's an analytic function, and therefore then f of x is given by this integral. So 1 by 2 pi integration from minus infinity to minus infinity. So there are two integrals here. So first the integral is two variables of integration. So we have two integrals. So first integration, the integral inside is on dt, the variable dt, and the integration outside is on d lambda, the variable is lambda. So f of t cos lambda t minus x. So this is the Fourier integral. So if you were to write the complex form of the Fourier integral, the complex form would be f of x 1 by square root of 2 pi, again two integrals, so we have these two integrals. So we'll use this to solve some problems. So and before that, let me also give you the Fourier sine integral of f of x and Fourier cosine integral. So the Fourier sine integral is the Fourier sine integral is f of x is equal to 2 by pi 0 to infinity 0 to infinity f of t sine lambda t sine lambda x dt. So two integrals. The inside integral is on dt and the variable t, and outside is on lambda. So the cosine integral, Fourier cosine integral. This is the Fourier cosine integral. So we'll solve a problem using this Fourier integral. So we're asked to evaluate the value of, our problem is to find the value of find the value of 0 to infinity, integral 0 to infinity, sine lambda cos lambda x, lambda d lambda. So we have to find the value of this integral and another integral and other integral 0 to lambda sine lambda. Now we will do this by expressing f of x as a Fourier integral. So f of x is defined as 1 where modulus of x is less than or equal to 1, and 0 when modulus of x is greater than 1. So we will express this f of x as a Fourier integral, and then we'll find out these values. So this integral is evaluated by using this Fourier integral. So we'll see how we go about doing it. So let's write out the Fourier integral. So the Fourier integral we had said is nothing but this integral, right? So this integral. Now, and our given f of x is 1 only between where mod 1 is less than or equal to 1. So therefore, in our Fourier integral, this is, let me write out the Fourier integral. This is our Fourier integral. So the outside integral we will evaluate later. The inside integral we have to evaluate first. So in our given f of x, we are first evaluating. So we are first evaluating the inside integral, and in the inside integral, the given f of we'll use t here. Okay, so let's use t. So the in our given f of t, it is, so let me write out the integral. So given f of t is 1 between -1 to +1. So this integral minus infinity to plus infinity. This integral, let me write out this integral. Cos lambda t minus x dt d lambda. So first integral is over dt, and this given integral is value is 1 only for -1 to +1, and greater than that it becomes 0. So this integral will become only -1 to +1, and f of t value is 1. So just leave it as it is. Just put 1. Doesn't matter. Now you evaluate this integral. So you have to integrate cos lambda t minus x dt, okay, with respect to dt. So when you do that, so the outside integral will remain, and this when you integrate cos lambda t minus x, you have to integrate, so integration becomes sine lambda t minus x divided by the differentiation of lambda t minus x. So that will just be lambda. So differentiation with respect to t. So that will be an upper limit minus lower limit. 1 minus 1 d lambda. Now when you do upper limit minus lower limit, what we actually get is, this is what we'll get. So when you do upper limit minus lower limit, so let me write it out. So we get 1 by 2 pi minus infinity to plus infinity sine lambda minus lambda x plus sine lambda plus lambda x. Now this is of the form sine a minus b plus sine a plus b. Okay, so you take lambda as a and lambda x as b. So this sine a minus b can be now written as there is also 1 by lambda outside. Just keep the 1 by lambda outside. There is a 1 by lambda. Anyway, so there is a sine a minus b plus sine a plus b. So sine a minus b is nothing but we have to expand and write. So we should know the trigonometric formula. Sine a minus b is nothing but sine a cos b minus cos. So in the place of b we have lambda x, right? Minus cos a, which is lambda, and sine b, which is lambda x. Plus we have this is sine a plus sine b. So this is nothing but sine lambda, which is sine a cos b plus cos a sine b. So we have to evaluate this now. So this integral is to be integrated over d lambda. So now what happens? You can see naturally that this term cancels out with this term. Okay, so this integral just now becomes 1 by 2 pi. So left hand side we have f of x. So 1 by 2 pi minus infinity to infinity 2 sine lambda cos lambda lambda x divided by lambda. So the lambda, you have a lambda from here, divided by lambda d lambda. Now notice here that this function here that we have inside this sine lambda cos lambda x by lambda is an even function because cos lambda x is an even function, and then we have two odd functions sine lambda and lambda. So when you multiply two odd functions, it becomes even, and then even when multiplied with another even function, it remains even again. So therefore this this quantity is an even function. So I can replace this integral instead of integral. So this is by the property of definite integrals. When you're integrating with symmetric limits, a definite integral it is equivalent to evaluating twice that integral. So two times that integral of two times this integral evaluated between 0 to infinity. So by that property we have now written this. Now what we can do is we can cancel out this 2. So we will cancel out this 2 with this 2. Therefore what we'll have is 2 by pi. So 2 by pi is what we have. Now notice that you can now take we were asked to evaluate in this problem. When we started out, we were asked to evaluate this integral, right? This integral. So this integral now can be evaluated like this now. So 0 to 0, okay, so let me write it out here. So this integral now can be evaluated like this. So I can take the pi by 2 to the left hand side and 2 to the denominator. So this, when this goes here, this is become pi by 2 pi by 2 multiplied by f of x. So this integral is nothing but pi by 2 multiplied by f of x. And f of x is defined here. F of x is nothing but the given f of x was, so this was our given f of x. F of x was 1 when x was mod x was less than or equal to 1, and it was 0 when mod x was greater than 1. So we have evaluated this integral. So this integral value is pi by 2 when it is pi by 2 when, so it is, so the value of this integral is nothing but pi by 2 when x is mod x is less than or equal to 1, and 0 when mod x is greater than 1. Now we were also asked to evaluate another integral. We were asked to evaluate this integral 0 to infinity sine lambda by lambda d lambda. So what we can do is we can just put x is equal to 0 on both sides. So when we put x is equal to 0 on both sides, what we get is, so when we put x is equal to 0 here, on putting x is equal to 0, the cos term, cos 0 is 1. Okay, so cos 0 is 1. So when you put x is equal to 0, this cos term becomes 0. This so it becomes cos 0. So cos 0 becomes 1, and then you remaining you have sine lambda by lambda. So 0 to infinity, this is what you have remaining. And right hand side you have, so here you have to also put x is equal to 0. So we know when x is equal to less than or equal to 1, when mod x is less than or equal to 1, that means in between -1 to 0 to plus 1, the value is pi by 2. Okay, so the value of the function is pi by 2. So when if you put x is equal to 0, the value of the function is pi by 2 in that region, pi by 2 in that region. So because, so pi by 2 in that region. So therefore this is the value of this integral also. So we evaluated, these is our answers. So this is one answer and this is the other answer. So we've evaluated these two integrals using the Fourier integral.